At minus 30 degrees Celsius, donut battery retains over 99% of its capacity. And if you push in the opposite direction, heating the cells beyond 100 degrees Celsius, that's 200 Fahrenheit, the result stays the same, over 99% capacity retention.
Donut Lab sent shockwaves through the EV and energy storage industries by announcing a 400-way HKG solid-state battery capable of a 5-minute charge retains over 99% of its capacity retention in a 22FA 100-cycle lifespan equivalent to 100 years and mass production backed by the claim that it will be installed in Ver's electric motorcycle as early as this quarter. If these specifications are accurate and scalable, the technology would represent a revolutionary breakthrough for the entire industry. After interviewing the CEO and examining the underlying technology, experts conclude that either this battery will change the world within the next 3 months or it will make the CEO look foolish. If this statement is accurate, it does not describe a normal battery. It describes a system that appears to defy nearly every known limitation of modern energy storage. Extreme cold and extreme heat are where batteries usually fail first, where chemical reactions slow interfaces degrade and capacity collapses. Yet, Donut Lab claims the opposite. Stability where instability should dominate. That claim alone raises a crucial question. Is this the first solid-state battery proven to withstand real-world conditions, or are these figures taken out of their proper context? So, how did Donut Lab demonstrate 99% capacity retention? The first detail that truly warrants scrutiny is this Donut Lab's 99% claim is not centered on cycle longevity in the conventional sense. Unlike most battery makers who define capacity retention as the remaining energy after a set number of charge-discharge cycles at room temperature, Donut Lab uses the metric to highlight resistance to extreme temperatures. Based on the company's disclosures, the cell retains more than 99% usable capacity at minus 30 C, a condition under which standard lithium-ion batteries typically lose 30 to 50% of their effective energy due to sluggish ion movement and sharply increase internal resistance. At the opposite end of the spectrum, Donut Lab reports stable performance at plus 100 Ca range, where liquid electrolyte lithium-ion cells are prone to severe failure modes such as gas formation, separator deformation, or thermal runaway. Temperature resilience, however, is only one part of the story. Donut Lab also claims a lifespan of 100 full charge cycles. For comparison, a high-end EV battery pack is generally rated for 1,500 2,000 zero cycles, translating to roughly 300-500 zero kilometers of driving. Even lithium iron phosphate LFP cells, renowned for durability, rarely surpass 500,700 cycles in practical use. A 10,000 cycle rating would imply a service lifespanning generations approaching a century with daily charging. The company further advertises 5-minute charging from 0 to 100% and a gravimetric energy density of 400 Wh/G, about twice that of today's mass-produced LFP batteries, roughly 160-200 Wh/Cuddy, and well above most commercial NMC cells. Any one of these figures will be notable on its own combined they challenge long-standing assumptions about unavoidable trade-offs between energy density, charging speed, and durability if such results were achieved using conventional lithium intercalation chemistry. Skepticism would be unavoidable. Intercalation, where lithium ions slowly embed themselves into rigid crystal lattices, inevitably degrades electrode structures over time. Accelerated charging intensifies this damage, while elevated temperatures amplify it further. Donut Lab, however, suggests a fundamentally different operating principle. The technology is reportedly rooted in advanced nanomaterials research linked to Nordic Nano, implying a strong emphasis on engineered electrode surfaces. Many engineers speculate that the system relies heavily on pseudo-capacitive behavior rather than pure intercalation. In simple terms, instead of lithium ions forcing their way deep into crystalline structures, they rapidly bind to active surface sites, more like temporary surface attachment than permanent insertion. This approach allows exceptionally fast charge and discharge while greatly reducing mechanical stress on the material. Such a surface-dominated storage mechanism could plausibly account for both rapid charging and long-term durability. If ions are no longer repeatedly distorting rigid lesas, structural fatigue drops dramatically. Unlike traditional batteries, which must balance power against lifespan, a pseudo-capacitive system can theoretically deliver both. The all-solid-state design is equally significant. Removing flammable liquid electrolytes eliminates a major source of thermal instability. Solid electrolytes do not boil, vaporize, or generate combustible gases, making high-temperature operation far safer. That said, solid-state batteries introduce their own hurdles, particularly at material interfaces where poor contact can sharply increase resistance. At present, the most serious concern is a lack of independent verification. Donut Lab has yet to publish peer-reviewed data or allow recognized third-party laboratories to replicate its results. All performance charts remain proprietary or promotional. By contrast, well-funded solid-state developers such as Quantum Cape and Solid Power, both supported by major automakers, have spent years attempting to translate promising lab results into scalable manufacturing. Scalability is the second major warning sign. Battery history is full of startups that dazzle with coin cell demonstrations only to fail when moving to pouch or cylindrical formats. Producing uniform nano-engineered surfaces, flawless solid-state interfaces, and defect-free layers is manageable at the gram scale, but extraordinarily difficult at industrial volumes. Even minor yield losses can render mass production economically unviable. Another point of unease is the broader industry silence. Giants like KDIL, Toyota, and Tesla have collectively invested tens of billions of dollars in battery research. Toyota alone has spent over a decade developing solid-state technology and still forecasts cautious incremental rollout. The notion that a relatively small startup could outperform all of them simultaneously without prompting rapid acquisition or licensing efforts naturally raises skepticism among professionals. Some materials. Scientists argue that achieving 400 WHKG 5-minute charging and 100 cycles in a single system would contradict established electrochemical limits, unless critical trade-offs are being overlooked.